Does 1 equal 0.9999 to infinity? Or 0.11 to infinity? Equality or approximation? The sequel to the geometric proof. My motto? Plain honesty, simple truth, easy understanding. Does 1 equal 0.999 to infinity? That's the question. Our first task is to define precisely what equal means. 2n equals 2n. 2n plus or minus 1 equals 2n plus or minus 1. But 2n plus or minus 1 is not equal to 2n even when n is the largest known prime number p raised to the power of itself, which is to say that even equals even and odd equals odd, but odd is not equal to even no matter how large n. A visual demonstration was shown in the first video, so this one is to raise and address some basic issues plus extra numerical examples. Whilst I do not have the least problem at all with the above extract taken from Engineering Mathematics by K.A. Stroud, it still does not justify that 0.999 is exactly equal to 1, and that it is therefore not just an approximation. We need to dispel the Sonic Hedgehog mindset, which is that as soon as we write 1 equals 0.9999 on a piece of paper, that it goes racing off to infinity. It doesn't. It is a step-by-step division process that starts with the first 9, then adds on the following tail end 9s one after the other. It is just that conceptually the division can be continued indefinitely to infinity. Leonhard Euler covered the theory of infinite decimal fractions in his elementary algebra printed in 1770. When he died in 1783, he was so bored behind the pearly gates that he has continually performed the division at the rate of 1/9 a second ever since. To the present day, Euler has only calculated around 7.4 billion 9s, not even a drop in the infinite ocean of the number of steps. Now let's challenge the mathmagicians. Take a Bateman machine. Program it. Press calc. Display A ? Enter 0, press equals. Display 0.9. Repeatedly press equals. Display 0.999 to the limits of the calculator's display. Unlike long division, when the 9s are repeatedly produced at the tail end, Bateman's algorithm continually pushes the 9s in at the head end. The infinite expansion of the decimal fraction is not inherent in the equation and is entirely dependent on the will of man. The following 5 examples paint the picture. The challenge to the mathemagicians is: does the infinite decimal expansion so produced still equal 1 at infinity by their reckoning? What if the seed value was 0.01 instead of 0? Does this or any other seed value equal 1 at infinity? Slide 15 gives a derivation of the first few terms of the infinite series for 1/3 utilizing rational fractions. The rational fraction remainders, which are highlighted in red, are true submultiples of 1/3, and on division complete the infinite expansion at any step in the series. Slide 16 gives a derivation of the first few terms of the infinite series for 1 equals 0.9999 using rational fractions. Although the rational fraction remainders, which are highlighted in red, look like a submultiple of 1, they do not add further to the decimal expansion after division at any particular step, as does 1/3. Slide 17. If the previous slide demonstrated that 1 equals 0.9999, then this slide demonstrates that 0.111 also equals 1. The two starting rational fractions are identical to the previous slide, but have been reversed. The infinite decimal expansion obtained actually approximates to 1/9, which is in contradiction to the opening statement. The rational fraction remainders after division are approximating to 8/9 at the same rate as 1/9, but the last term can only ever be a 9 and not an 8. Of course, we haven't got a contradiction because what we are evaluating is that the reciprocal 1/n is equal to the summation of the reciprocal of n plus 1 to the power x for x equals 1 to infinity. Feeding 1/9 and 1/10 into the above equation equates to the following rational fraction expansion as shown. The infinite series given in 18 and 21, derived from the principles of division of a rational fraction, have a remainder that is a submultiple of the original fraction and supply the balance of the digits of the infinite expansion directly, that is 1/300th and 1/900th. Partitioning of unity in 19 and 20 gives a rational fraction remainder that on subtraction from 1 gives the first set of digits already obtained, but does not divide to give the n digits, so the remainder can never be eliminated. Examples: 0.111 plus 0.889 equals 1. 0.112 plus 0.888 equals 1. 0.999 plus 0.001 equals 1, and 0.001 plus 0.999 equals 1. No matter how great the expansion and how small the remainder, it can never be eliminated. Hence, 0.999 is only an approximation to 1. Also, multiplying it by 1/3 is not equivalent to 3 times 1/3 as an irrational fraction. Mathmagicians' proof that 1 equals 0.999. Since 11 plus 1.1 divided by 11 times 1.1 is equal to 12.1 divided by 12.1 equals 1, therefore 1 equals 0.9999, because 1 over 1.1 is equal to 0.90909090909, and 1 over 11 is equal to 0.0909090909, and 1 over 1.1 plus 1 over 11 equals 0.999999. End of slideshow.